of this which says, well, we want to fit the data, so we do want to make this small, but we've got errors in the data, and so we don't want to strive too hard to fit the data at the expense of getting a ridiculous solution. And of course, what happens in this ill-conditioned system is that because there are some components of the X that produce very, very small changes in B, then the components of those will be determined by the errors in B. And the small errors in B will produce very big and spurious components in X. And because if we just allow any X, then they'll get very, very large. And so we'll end up with some very, very large components in X if we just do that. And we'll fit it very well, we'll manage to minimise this, but it will be rubbish. So the simplest approach to that is to have a bit of a trade-off between fitting the data and having a completely daft solution. So the trade-off that we do in Tikhonov regularization is to say, well, let's fit the data, but not if X gets too big. So what we do is we make some small positive number alpha, and we choose the matrix L, and just for the moment think of that as the identity matrix, so this is just norm X. Then this says, fit the data, but if X gets really, really large, and so that dominates the alpha squared, which is small, then we don't want to go there, right? So this trades off fitting the data against having a small norm of X. Well, having the L there generalises slightly the idea of norm, and I'd just like to invite you to think of one special case of that. If we maybe have pixels for our conductivity, so constant in squares or cubes, then we might want to say that the conductivity image is quite smooth, and so nearby pixel values are more likely to be the same as each other as further neighbours. In other words, there's not great big jumps. And that rules out the conductivity that, one pixel is, 10 million, and its neighbours are 1. So the way to penalise that would be to use a matrix L that takes a difference of neighbours. Right? And so the norm of the difference of the neighbours is small, enforces you can't have an enormous spike because that will be different from its neighbours. So we might use L as a difference operator between neighbours. Or you can use higher derivatives, or the identity, but for the moment this will do. And so the Tikhonov regularized solution is the minimum of this, and I'm assuming various things, that this has a minimum and it's unique, right? But to come to that in a moment. Well, of course it's still positive, so if there is a unique critical point it will be a minimum. And I was trying to think of the neatest and quickest way to do this, because what I'm doing is trying to take a path to the quickest way in which people can do EIT from this. And then let's go back and think about the details. So the quickest way to understand this is to derive this one from this one. So a typical constructive laziness of a mathematician. I'm going to define A tilde to be the matrix A alpha L, where I mean the block matrix with alpha L put underneath that. Now, of course, you hit this with a vector x, so L is a matrix that you hit with L, with L is a matrix that you hit x with, so it's the right size. I mean, depending on which differences we take, could be different length, but we're actually adding more equations in this. And then I define B tilde for the moment to be the vector which is B with enough zeros padded on to make it the same length. And then if you consider A tilde times the normal x is equal to B tilde, well, or maybe perhaps if I can just modify that, if I consider that, because we're trying to find a least squares solution, then of course that's AX and that's alpha LX. So this is the norm squared of the vector which is AX minus B and alpha LX. And because I'm using the Euclidean norm, the sum of the squares of this, I can add up those components and those components, and so that's just the norm. Okay. So minimizing that is the same as minimizing that. And I already know how to do this because I just plug it in the original formula. So now, A transpose A, I suppose I'd like to draw a picture of it. A tilde transpose A tilde would look like A alpha L times that's transpose, that's transpose. So that's A transpose A plus alpha squared L transpose L. L didn't need to be squared. Okay. So I've got A transpose A as an alpha. And then A transpose, A tilde transpose B tilde, that's just A transpose B. Okay, so let's just think about if this makes sense. I'd assume that A already had rank n, it just had a small condition number. So if I add some more equations, it's still got the same rank. The point is, intuitively, I think you can see that if I say took L to be the identity or something that was relatively easy to invert, then I'm adding some nice equations. Right? So actually the condition number of this, if it was very small, the condition number now depends on alpha, and the condition gets better as alpha gets bigger. We're adding more of this nice invertible, or actually it doesn't have to be invertible, but if it's got a null space, it has to be one that was something that was relatively easy to solve A for that component. So typically you take a difference, it might have constants in the null space. Okay, so this has made the matrix better conditioned, and I mean certainly it's still invertible if A transpose A was, and so now this is the Tikhonov regularized solution, and we have the problem of choosing alpha, and we'll want a bigger alpha if we've got more errors in our data, because it's a trade-off between fitting the data too much and getting a ridiculous solution. So there's a whole kind of there's a list of methods and there's various kind of debates about how you choose this so-called regularization parameter. But this is the simplest thing that people try for an ill-posed problem. It's a kind of first reaction. It's regularly reinvented, so it has lots of names. In statistics, they call it ridge regression. It's sufficiently simple and intuitive that it's very widely done this way. And that's what probably most people do EIT this way. Now, as a slight digression, there is also a statistical interpretation of this, and the interpretation is that if the errors on the data B are normally distributed with mean 0, and you assume that the prior information about x is something proportional to e to the minus alpha squared norm lx squared. In other words, rather than assuming that x is completely arbitrary, and we've already said we want to rule out, ridiculously large spikes, that if you assume that x is drawn from a probability distribution that's distributed like this, which is kind of normal distribution with a different covariance matrix, looks like normal, then we've got two sorts of probability. On the one hand, the distribution of errors from our experimental apparatus. On the other hand, a probability distribution that represents our belief about the solution x before we start, a so-called prior distribution. And if L was differences in their neighbours, this says it's more probable that neighbours have similar values than different values. Right? So if you put those together and you use Bayes' theorem, which tells you how to work out conditional probabilities, then you can write down what's called the MAP estimate, maximum a posteriori estimate. And what that is given that you've got a prior distribution and a distribution of errors, you look at the probabilities of